Greetings, welcome to the 17th lesson in series of lessons on basics of power systems engineering. This presentation is part 3 of a 3-part lesson that covers power in single-phase AC systems. This lesson covers power triangles and use of capacitors in improving the power factor of inductive loads. An inductive load is a type of load that consumes reactive power and has a lagging power factor. As an example, the diagram on this slide shows an inductive load, shown here, that is connected to a voltage source through a line that itself is an inductive line based on its impedance. Since loads in general can be sensitive to line voltage levels, it is common practice to keep the voltage at the load side at a constant, which is called a nominal voltage, as much as possible, and determine the voltage at the source that is needed to support such a fixed voltage at the location of the load. I will keep the voltage across this load at 220 volts and will designate it as the reference voltage with 0-degree phase angle. So the voltage at the load would always be 220 volts with 0-degree angle. Let's find the current given the voltage here. I equals this voltage, 220 with 0-degree angle, divided by this impedance. And this ratio, V over Z, will give me the current through this load, which would be the same as the overall circuit current that goes through the source and through the line as well. 220 over 20 plus J23 comes to 7.218 amps with negative 49 degrees of phase angle. Having the current, we can now find the source voltage by first finding the voltage drop across the line, across here, and adding it to this 220 volts that was the voltage of the load. Here it is. V source equals I times this quantity plus the 220 voltage of the load, which is written right here. The sum of those two, which defines the source voltage, comes to 251.4 volts with 1.835 degrees angle. The loaded voltage at the receiving end is of course 220 volts by design. But if I remove the load from this circuit, the entire Vs will show up at the receiving end, because if this is removed, the current here drops to 0, and the voltage Vs, which we found to be this value, will directly show up where the load was located before I removed it. This voltage is known as the no-load voltage, and the percentage change of the voltage between load and no-load values is known as voltage regulation. I'll find the voltage regulation for this circuit. So voltage regulation is defined as voltage at no load minus voltage at full load divided by voltage at full load. We have all the values. I have to emphasize that we only use the magnitudes for these. So the magnitude of no load voltage is 251.4, and the magnitude of the full load voltage is 220. Substituting those, we get VR, or voltage regulation, equals 14.3%, which is not a good voltage regulation. Anything above 7 or 8 or 10 is considered to be poor voltage regulation. Let's next determine the power factor of the load. One way of finding the power factor is to take the cosine of the phase angle difference between voltage and current. Here the difference between the phase angles of the voltage and current is 49 degrees because the angle for the voltage is 0. Cosine of 49 gives me 0.656 for the power angle, for the power factor of the load, and we'll designate it as lagging. Lagging because the current lags the voltage. You can see that the voltage has a 0 for its phase angle, and the voltage has a negative number for its phase angle. So the current is lagging the voltage, and therefore the power factor is designated as lagging. 0.6556 is a poor power factor. Power providers give incentives to their customers to maintain their load power factor much higher than this. Let's summarize the results that we have found so far so that we can refer to them later. Here are the current, the source voltage, the voltage regulation, and the power factor. Of course, the load voltage is a constant 220 with 0, and the load impedance is written out up there. I will now find the real and reactive powers that are consumed in the load and that are lost in the line. To find the real and reactive powers used up in load and in line, we can find the complex power as V times complex conjugate of I, and then take the real and imaginary parts of it as real and reactive powers respectively. However, I'm going to take a more direct route here, and that is to multiply each impedance by square of the magnitude of the current that goes through it. For example, the real power consumed in the load would be 7.218 squared times 20. 7.218 is the magnitude of the current. Square that and multiply it by 20 will give you the real power consumed in the load. Here it is. And for the reactive power of the load, same current squared multiplied by 23. Again, magnitude of I is 7.218. Square it and multiply it by 23 to get the reactive power, and that has come to 1198.3 VARs. In a similar way, the real and reactive power losses in the line are also calculated. So again, current squared times 2 gives me the real power loss of the line, and current squared times 4 gives me the reactive loss in the line. These are the results so far and their calculation. As an exercise, you could find the complex power of the source by multiplying the source voltage V sub S times the complex conjugate of the current. And you should get these two numbers as a check. The V sub S is given here directly, so we'll use that. And I conjugate is simply this value, but with the sign reversed from negative to positive. So I asterisk would be 7.218 with positive 49 degrees. And if you multiply those two, you'll get S, which is the complex power, which is P plus JQ. P should come to this value, the source real power, and Q to this value, the source reactive power. Let me just summarize the results that we found so far. Here they are, all of the powers. that were calculated, and the current, source voltage, voltage regulation, and power factor. A good way to visualize the relationship between real, reactive, and apparent power is the use of something called a power triangle that is constructed on a perpendicular set of power axes shown on the next page. The axes are the horizontal one for real power and the vertical one for reactive power. The way to construct this triangle, which is called the power triangle, is to mark the real power. I'm doing this for the load right now, for the powers of the load. To mark off the real power of this load over on the horizontal line, which is 1042, and to mark off the reactive power of the load, which is 1198.3 VARs on the vertical axis. Find the point on the plane and connect the origin to it. You get the hypotenuse of this right triangle, which will then give you the apparent power. The apparent power can be found as square root of, well, let me write it as, first of all, S equals P plus JQ, and which means that S squared equals P squared plus Q squared, which is the Pythagorean relationship or equation for this right triangle. Another way of finding the apparent power is to multiply the magnitude of the voltage, which was 220 for the load, times the magnitude of the current, which is 7.218. So if you multiply these two, you should get this number as well. The angle between the hypotenuse and the real axis is the power factor angle. This angle here. The cosine of this angle will give you the power factor. So if I call this alpha, power factor equals cosine of alpha, which from this triangle it would be 1042 over 1588. And if you do the division on your calculator, you should get this number, 0.656, for the power factor. We're about halfway through this lesson. I would like to take a short break at this point to introduce myself before continuing on with the rest of this presentation. My name is Fuad Albandi. I am a PE in Electrical Power Engineering. This is the 17th lesson in a series of lessons on basics of electrical power engineering that I have published on the YouTube. You'll find my name, email address, and my web address on this page. I invite you to visit my website for comprehensive modules on power systems engineering topics. My website is own-your-destiny.mylearnworlds.com. I will now continue the work with our example from where I left off. To focus on the load power, I will delete the other calculated powers for now. So I'm just listing the load powers, the real, reactive, and apparent load powers, which you also see the values you also see on the power triangle. In order to increase the power factor and bring it closer to 1, we can add a capacitor to this circuit in parallel with the load. Capacitors supply reactive power, which is used locally by the parallel inductive load, thereby reducing the overall reactive power demand from the source. The fact that the source has to transmit smaller amounts of reactive power to the load will cause the line losses to go down and will improve the voltage regulation, as it will be seen by the end of this presentation. Let's assume that we want to raise the power factor from 0.656 lagging to 0.95 lagging. Here is the circuit with the capacitor installed. I'm going to give a value of C to this capacitor, and we'll find that value in a little bit. The real power consumption of the load will not change, of course, in this combination. Once the capacitor is installed, the real power use of the combination would be the same as what it was before, which was 1042 watts. The things that will change are the total reactive power consumption, and along with it, the apparent power will also change. First, let's find the apparent power for the combination of load and capacitor. We know that real power divided by apparent power gives the power factor. So the real power does not change, so it's 1042 divided by the apparent power of the combination of the load and the capacitor will give me the power factor, which I want it to be 0.95, so I'll set that equal to 0.95. Finding the new value of S for the combination of the load and capacitor from this equation will give me a value of S that's 1096.8. This is the combo, and we know the relationship between S, P, and Q is S squared equals P squared plus Q squared. For this smaller triangle, now I have the S and we have the P, because the P hasn't changed, and the S we have found is 1096.8. So having those two, I can calculate Q as the square root of S squared minus P squared. This gives me the Q reactive power usage of the combination of the capacitor and the load. And here I've done it over here, and the answer comes to 342.4 bars, which means this height here is going to be 342.4 bars. The capacitor will then need to provide the difference between these two. In other words, this delta Q would be what the capacitor needs to provide, Q sub C. And that difference comes to 856 bars. We were here before the installation of the capacitor. We would like to be here after the installation of the capacitor. So the capacitor will need to provide this much volt ampere reactive, this much reactive power, which was calculated here. So we now have QC, Q sub C, or the power that the capacitor has to provide. Just as I squared Z gives the complex power, V squared times complex conjugate of admittance also gives the complex power. Let me just write this out. The complex power S can be calculated as I squared Z, or it can be calculated as, so if we have the current through an impedance, we can use this. If we have the voltage across an impedance, we can use V squared times Y conjugate to get the complex power. This is what I want to use here for the capacitor. The admittance of a capacitor is J times omega times C. Its complex conjugate then would be negative J omega C. However, since we are working here with the magnitudes of the reactive power, the equation simply becomes Q equals V squared times omega C, which you see here. Technically, there is a negative J here, but again, we're only looking at the magnitude of the reactive power here. Substituting for V and omega as 2 pi times frequency, and having QC from here, we can find the value of the capacitor. So from this equation, we will find the C, as you can see here, equals QC over 220 squared over 2 pi times 60, assuming 60 hertz frequency. And the capacitance comes to 46.93 microfarads. Now, having the capacitor value and the load value, we can find the current through this new circuit. Once again, assuming that the source voltage is adjusted so that the load voltage is at 220 volts. First, let's find the current by first finding the two admittances, adding them together, and then multiplying the combined admittance times the voltage to get the current. Here is the admittance of the capacitor alone, J omega C, substituting all the values that we have on the right hand side. The capacitor admittance comes to J 0.01769 Siemens. We'll add that admittance to the admittance of the load because they're parallel. The admittances add when you have two elements in parallel. So the overall Y, overall admittance of these two, is going to be equal to YC, which was found here, plus 1 over Z, and that total comes to this value for the admittance of the two together. Current into the combination is found then by multiplying the voltage of 220 times this combined admittance, because we know I equals V times Y, and we have everything that we need on this side. V is 220 with 0. Y was just found for the combination from here. And the current comes to 4.985 with negative 18.167 degrees. You can see that the current magnitude has gone down from 7 something that it was for the circuit without the capacitor, and it has come down to 4.985. Let's find the different powers of this combination circuit. For the line, we have I squared times 2 for the real power. I is here is 4.985, so we'll square that times 2, and we get 49.7 watts of power used up in the line of real power. And same current square times 4 gives us 99.4 watts of reactive power consumed in the line. Next, I'll find the load power. Well, actually, the load real power it has not changed, so it's 1042. I don't need to recalculate it. And the combination reactive power is simply 342.35, because that's what we had designed it to be for the 0.95 power factor. The source power is, as usual, is the sum of the two powers. And here they are, the real power of the load and the real power loss of the line added together gives me the source real power, and the sum of the imaginary parts of the line and the load gives me the total reactive power that the source has to provide. Let's start with the current now and find the voltage drop here so that we can also calculate the voltage regulation. The current we already have. Multiplying the current by the line impedance gives us the voltage drop here. Add that to 220 with 0 to get the source voltage. And the source voltage is 236.2 with 3.844 degrees. We can find the voltage regulation now. And VR again is voltage at full load, which is this, minus voltage as no load, which is 220, divided by voltage at full load. I wrote this backwards. It should be voltage at no load minus voltage at full load divided by voltage at full load, so that the numerator comes out positive. And so 362 for no load minus 220 for full load divided by 220 times 100 gives me 7.36%. I'll now compare the quantities that were found for the original circuit to those found after the introduction of the capacitor in two columns. So on the left hand side we have the values without the capacitor, and the right hand side we have the values with the capacitor. And of course the real power has not changed. The Q load has gone way down for the combination of the capacitor and the load. The line power, real power loss has gone down almost to half. The reactive power loss of the line has also gone down from 208 to 99. The source has to produce less power, less real power, and also less reactive power. You can see the source power, real power, has gone from 1146 to 1091 to 1091.7, but that's not surprising because the loss, real power loss of the line has gone down, and same with the source reactive power has gone down from 1406 to 441. This should be a var, it's a typo. And the current has gone down in magnitude from 7.218 to 4.985. The source voltage has also gone down from 251 to 236. Voltage regulation is cut almost in half from 14 to 7.4. And the power factor, of course, has gone up because that was the purpose of introducing that capacitor, to take it from 0.656 to 0.95. We are now at the end of lesson 17. If you enjoy watching my channel, please click on the subscribe button and the notification bell. If you're looking for a resource to review topics in preparation to take the PE exam in electrical power engineering, you'll find the modules on my website to be useful. Thanks for watching this video, and I hope to see you soon in another one of my presentations.